Yep, I'm live it seems. Probably I am. And yes, I am live. Now, today we will continue. And what were we learning yesterday? Yesterday we were learning about general input-output interfaces which have pins. What were they called? Yesterday was the first time that I saw that there is something like this. These interfaces, they have pins which come out like physical pins which can be on or off. uh, GPIO, general purpose input output. These devices have physical pins which have like literal physical pins to which other devices like a light bulb, a switch, or sensors can be connected, and depending on the registers which are inside these devices, those pins are either on or off or in some more complicated state depending on the type of pin that it is. And by switching the contents, the binary contents of their internal registers, you can change the state of those pins and thus communicate with the outside world using these pins. But since you have to manually change the binary stuff, that is why these are slow. But for things like a mouse, a keyboard, a monitor, you can have standardized ways to communicate between the processor and the device, that is your monitor, mouse, or keyboard. These are called human interface devices, HIDs, and they have their own standards to talk to each other, which is faster and does not rely on general purpose. It is very specific purpose standard and much faster and much better. Now, today, GPIO in a Raspberry Pi. Let's see the Broadcom. Broadcom is a company which manufactures the processor for a Raspberry Pi. Raspberry Pi, not Raspberry. Raspberry Pi. Broadcom, this system on chip, which is used in Raspberry Pi, contains 54 GPIO pins, okay, which are split into two banks. The GPIO pins on these systems are named using the following format: GPIO-X, where X is the number between 50 and 53. That is a very complicated way to name a pin. The GPIO pins are highly configurable. That is why they are GPIO. Each pin can be used either for general purpose IO or can be configured to set up to 6 predefined alternate functions. Configuring a GPIO pin for an alternate function usually allows some devices within the BCM this to use the pin. For example, GPIO 4 can be used for a general purpose IO to send the signal generated by the general purpose clock 0 to external devices, to send bit 1 of the secondary address bus to external devices, or to receive GTAG data for programming the firmware of the device. Uh, okay, and with this chapter number 11, my goal is to get a overall understanding about how devices are connected to a computer, and that is it. And if I ever were actually coding and writing all of that, then I can continue over that and go deeper. But for now, my goal is to understand it from the surface because I do not actually need this right now. But it is a good thing to have knowledge about stuff like that. This is interesting. The last 8 GPIO pins, this have no alternate functions and are used only for GPIO. Okay, in addition to the alternate function, all GPIO pins can be configured individually as input or output. When configured as input, a pin can be configured to detect the signal changes and send an interrupt to the CPU. Each input pin also has internal pull-up and pull down registers, which can be enabled or disabled by the programmer. Okay, these are highly configurable and can be individually set to receive data. The GPIO pins on BCM28 and XX system on chip are very flexible and quite complex, but are well designed and not difficult to program. Once the programmer understands how the pins operate and what the various registers do, there are 41 registers that control the GPIO pins. The base address for the register for the GPIO device is this, and with an offset, I can access all the 41 addresses. The 41 registers and their offsets from the device address are shown in table 11.1. This, which is just on the next page. Hmm. This is the off. These are the offsets from the base address, and this is the name of the register, and these are the sizes. I should have 51. And these are the permission: read, write, read, write. Here is only write and here is only read. These are crazy registers. Now, setting the GPIO pin function. The first 632-bit registers in the device are used to select the alternate functions for each of the 54 GPIO pins. The function of each of the pins is controlled by a group of 3 bits in one of these registers. Okay. This is very specific to how GPIO input and output is done in Raspberry Pi. At this point, I get the theory of how GPIO works, so I can move on. Detecting GPIO events. Okay, and this would be very easy if I were doing this right now, but I do not have a Raspberry Pi right now with me, right? So I'm not going to give my time to something that I do not want to learn, but I might learn in the future when I actually want it. And then I will be more interested and I would go much deeper. And that is the thing. If I were to go in this deeper, which I first of all do not want to learn, which is not a big deal, but second of all, I actually do not need to learn about GPIO pins, general processing input output, because I do not actually need it right now. So I can move on. Pulse modulation, that is a thing which I might want to learn about. The GPIO device provides a method for sending data signals to the external device. This can be useful to control devices that have basically two states, on and off. In some situations, it is useful to have the ability to turn a device on at varying lengths. For instance, it could be useful to control a motor at any required speed or control the brightness of a light source. One way that this can be accomplished is through pulse modulation. And this GPIO section would be very fun if I actually had a Raspberry Pi and some devices to go along with it. A Raspberry Pi plus a motor and a Wi-Fi connector. I actually have a Wi-Fi device. I do not know how that would be connected with the Raspberry Pi, but I guess Raspberry Pi comes with its own Wi-Fi thingy. But what I can do is make a remote with the Wi-Fi device that I have, attach it to some other Raspberry Pi, but and put a on off switch, and I can from my remote operate the other Raspberry Pi, which would be connected to a motor, and whenever I click on or off, that Raspberry Pi would turn on that motor, and that motor would have a coil around itself, around its head, which would rotate, and it would, on the other end, the coil would be looped around a doorknob, and when the motor when the core of the motor rotates, the doorknob will also rotate, and thus the door will be unlocked. and if I press it again, it will rotate in the opposite direction. Thus, the door will be locked. So I can control the fact that I can lock and unlock my room sitting over here just by a button. That would be crazy, but I do not have a Raspberry Pi right now, so that is also that might be a slight convenient inconvenience. But pulse modulation, yeah, pulse modulation. I can increase or decrease the pulse, the rate at which I am sending signal. I can skip all of this because I'm not going to use it, and probably I will just spend my take a long time to actually read all of this and understand this, and I will eventually forget it because I'm not using it. And instead, I can skip over to things that I actually want to use. There are some classes or devices that are found in almost every system, including the smallest embedded systems. Such common devices include hardware for managing the clock signals sent sent to the devices and serial communication, typically RS-233, 232. Most mid-sized or large systems also include devices for managing virtual memory, managing the cache, driving a display, interfacing with keyboard and mouse, accessing disk and other storage devices, and networking. Small embedded systems may have devices for converting analog signals to digital and vice versa, pulse width modulation, and other purposes. Some systems, such as the Raspberry Pi and Pecduino, Pecduino, not Arduino, Pecduino, have all or most of the devices of large systems, as well as most of the devices found on embedded systems. This chapter will look at two devices found on almost all system networks: clock management device. Okay, I want to read this again. There are some classes of devices that are found in almost every system, including the smallest embedded systems. Such common devices include hardware for managing. Okay, such common devices include hardware for managing clock signals sent to other devices, and serial communications, typically RS-232. Most serial communications RS-232. What is RS-232 serial RIAL communication? What is RS-232 serial communication? RS-232 recommended standard. 232 is a standard for serial communication that defines how data is transmitted between devices. It was originally established by the Electronics Industries Association (EIA) in the 1960s and is commonly used for communication between computers, microcontrollers, and peripheral devices. Okay, computer includes my memory, input output. Computer is the whole thing: memory, input output, and the CPU, or maybe they are just referring to the CPU when they say computer. And by CPU, I mean control unit and ALU. So, and what are microcontrollers? I have seen that term before, but do not know exactly what that means. Moving on, key features of RS-232. It is a recommended standard through which we can communicate between devices. Asynchronous communication: data is transmitted a shared clock, without a shared clock, using start and stop bits for synchronization. Full duplex can send and receive data simultaneously. Voltage levels: using high and low voltage to represent binary data. High is this, uh, low is this. High voltage represents 0 and low voltage represents 1. That is absolutely crazy. Baud rates. Common baud rates include this. I do not know what is baud rates. Point-to-point communication typically connects only two devices. Example, a computer to a modern microcontroller. To a modem or microcontroller. What the fuck is microcontroller? Connector types uses DB 9 pins or DB database 25 pins connector signal lines. All of these. How RS recommended standard 232 works. Data is sent bit by bit over a single wire. Data is sent bit by bit over a single wire. Okay, that makes sense. Single wire, they mean embedded wires inside the motherboard, inside the PCB. Then each byte of data is framed with a start bit 0, 8, 5 to 8 data bits, an optional parity bit, and one or more stop bits. Devices must agree on the same settings, baud rate, parity, data bits for connection. Each byte of data is framed with a starting bit. Each byte of data is framed with a starting bit, an optional parity bit, and one more stop bit, which tells that data, this byte ends here and starts here. Industrial automation, networking, embedded. Okay, first of all, what are microcontrollers? Then what are baud rates? And then why does low voltage levels represent 1 and 0 is represented by high? Well, why would they make this unobvious choice? Now, first of all, this uh, what are controllers? What are microcontrollers? Microcontrollers. A microcontroller (MCU) is a small, self-contained computer on a single integrated circuit designed for controlling electronic devices. It contains a processor, CPU, memory, RAM, and input-output peripherals all in one chip. Key microcontroller, don't they mean just a microprocessor? CPU, central executes instructions. CPU, okay. Oh, there are differences. Okay, we will get to that. It has a memory, RAM, and ROM, and has I/O ports for sensors, LED motors, time controllers, serial communication interface. RS232 is one of them. ADC, analog to digital converters. PWM, pulse width modulation, and interrupts allow the MCU to respond to external events quickly. Definition: microcontroller, self-contained system with CPU, memory, and I/O. Processor requires external memory and peripherals. Okay, microcontroller has everything. Like it is a small computer in itself. Usage: embedded systems, automation, IoT, computers, smartphones, servers. Microprocessor takes high power. Microcontroller takes low power. Examples: Arduino, etc., and Intel. Okay, yeah, that makes sense. Microprocessor does not has its own memory and its own input output devices, but a microcontroller has its own memory and input output devices. Common microcontroller families: Arduino, Texas Instruments is a, I believe, a Chad company, and ARM Cortex M series. Applications: home automation, robotics, automotive systems, industrial automation, consumer electronics. Okay, I get what are microcontrollers. Now, what is baud rating? But before that, this: why is lower? Why are lower voltage levels used to represent a binary 1 and higher voltage levels to represent a binary 0? Yep. In RS232 serial communication, a binary 1 mark is represented by a negative voltage, while a binary 0 space is represented by a positive voltage. This might seem counter. No, 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 no. Higher voltage means higher number of electrons, and negative voltage means positive, positively charged wire, which would attract electrons from a high voltage wire, which is highly negative charged and is ready to throw it electrons left, right, and goddamn center. This might seem counterintuitive since many other digital systems use high for 1 and low for 0. The reason for this convention dates back to the design of the early telegraph and serial communication systems. Reasons for using low voltages for binary 1 and high voltages for binary 0. Historical telegraph influence current loop logic. Historical telegraph influence current loop logic. Early telegraph and serial communication systems used current loops instead of voltage levels. A current flowing on was considered a binary 0 active, while no current off was 1. This convention was carried over into RS recommended system 232, where negative voltage represent idle mark and positives represents 0. But why was in the early systems 0 taken as on current was taken as a 0? Noise immunity. RS232 was designed for long distance communication over unshielded cables. Electrical noise in the environment tends to pull voltages towards 0 due to magnetic interference EMI. With using a negative voltage for idle 1 ensures that noise does not mistakenly cause false signal transitions. Compatibility with vacuum tubes and transistor logic. Early computers and peripherals used negative logic with. Why did they use negative logic? Negative logic means lower voltage means a 1, a binary 1, and higher voltage represents a binary 0 with vacuum tubes and bipolar junctions. Transistors, BJTs. In many of these systems, negative voltage was easier to use as an idle state due to the way transistors switched currents. Hmm, 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 hmm. Hmm. It seems like it is more because of convention than because of some technical things. Now, moving on to the third thing, bow baud rate. What is baud rate? What is baud rate? Baud rate explained. Baud rate is the rate at which data is transmitted in a communication channel, measured in symbols per second or baud. In serial communication such as RS232 and others, baud rate determines how fast bits are sent over the connection. Isn't that just equal to clock speed? Because clock speed determines how quickly you can change the state of a transistor, and thus you can change the state of the output wire. Baud rate versus bit rate. Baud rate refers to the number of signal changes symbols per second. Bit rate refers to the number of bits transmitted per second. Number of bits transmitted per second. And baud rate refers to the number of signal changes symbols per second. Hmm. In simple system like RS231, one baud rate equals 1 bit per second. It should be equal to, right? If no, one baud means I am changing the signal once every second. Then Yes, I am sending 1 bit of data every second. However, in more complex systems where where multiple bits can be encoded in a single signal, change bit can be higher than baud rate. Okay. Baud rate does not mean the change in bit. It means the change in the symbol that is going on. But a symbol, maybe if there are two wires, then the bit rate would be higher, but the baud rate would still be same. Standard baud rates used in serial communication. Higher baud rates allow faster communication but may introduce signal integrity issues over long distances. Why is baud rate important? Device synchronization. Both sender and receiver must use the same baud rate to properly encode data. Speed versus reliability trade-off. Higher baud rates increase the speed but can cause errors if the connection is noisy or unstable. Determining data transmission time. A higher baud rate reduces transmission delay. Okay, yes. Example, calculating data transmission time. If you transmit 8-bit character with one start bit, no parity, and one stop bit, then total 10 bits at 9600 baud, the transmission time per character is, wait, if I'm sending 10 bits and 9600 is my baud, which would mean I can send 9600 characters per second, then one character would take 1 upon 9600, 10 bits upon 9600. This millisecond per character. Bits divided by this bits, this baud. Would you like an example of baud rate in Arduino and Linux serial communication? Okay, I'm sending 10 bits. 10 bits represent one character. Yeah, and this is the amount of bits that I can send. Okay, let me see. So, um, however, however, I am sending data over a network, 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 I will always be using, let's say, wires and a wire. I will always, let's say for wires, when sending data through wires, a wire at a given moment can only be in a given state, can only be in a given state, either high or low, and bit rate represents how how many times the wire can change its state in a second, and baud rate, no, wait, shit. Bit, nope, not bit rate, but baud rate represents how how how, how many times the wire can change its state in a given second. rate represents how many bits are being transferred in a given second. And now, if if the system has only a single wire, then the baud rate and bit rate would be same. But if the system has multiple wires taking out data, or taking in, but okay, taking out data, then the baud rate would be the same as for a single wired connection, but the bit rate would be higher for higher number of wires. Is that correct? You're on the right track. Let's redefine your understanding a bit more. No pun intended. About rate versus bit rate in different systems. You are correct that if a system has only one wire data transmission, like traditional serial communication, bit rate, baud rate equals bit rate, because each signal change symbol carries exactly one bit. Yes, each symbol carries exactly one bit. However, when multiple wires or advanced encoding techniques are involved, the bit rate can be higher than the baud rate. Single wire, simple serial communication, that is no encoding, I guess. A single wire can only be high 1 or low 0 at any given moment. Each signal change represents exactly one bit. Yep. If baud rate is 9600, then bit rate would also be 9600. Parallel communication, multiple wires. If you have n wires transmitting data simultaneously, each wire carries a separate bit per baud. Per baud, each wire carries a separate bit. Example, if you have four wires, each transmitting at 9600 bauds, then the bit rate would be four times of that. Scenario 3, advanced encoding, multiple bits per baud. Some systems like COM in modern or Manchester United encoding in Ethernet encode more than one bit per change. How? Example, if a system uses four voltage levels, each level can represent two bits. Yep, yep, yep. A system running at 9600 baud, but encoding two bits per baud would have a bit rate of two times. Bit rate equals baud rate into bits per symbol into number of wires. Would you like to example of a real world example? Okay, baud rate is that, and the baud. Wait, why is it called baud rate? Was it invented by someone called baud? Yes, it was invented by someone called Baudot. Baudot, a French telegraph engineer who invented baud coding, an early character encoding system used in telegraphy. Why baud? Why baud? That's the man. In early telegraph systems, a symbol was the basic unit of transmission. Emily Baud, wait, a French telegraph engineer. Emily, that is a female. That is even more cooler. Emily Baud's, like Grace Hopper. Emily Baud's telegraph system transmitted characters using fixed length symbols instead of Morse code's variable length, dots and dashes. The unit baud was later adopted to measure the number of symbols per second in communication. Baud rate definition, baud rate refers to that. And yep, how she did pretty early. Baud code 1800s. When was when was Morse alive? Morse was alive, I guess. He was born in late 1790s. I guess he he was born in what I remember. He was born in 1793 and died in 18th century something. George Morse, Gregory Morse, George Morse, American film director. Ah, Morse, um, um, Morse person, Samuel Morse. Yes, Samuel Morse, 71 and died in 72. He was born in 91 and died in 1972, 27 April. Died on 2nd April. Well, one day after April Fool. So people didn't believe, I guess. Now, yes, baud rate. Now, clock cycle. The baud oh, rate of a device would be equal to the clock cycle if no complex encoding is used. That is only a single symbol represents only one bit, and no matter the number of wires, the baud rate would be equal to the clock cycle. Yes, you are absolutely right. Let's break it down in a structured way to reinforce my understanding. Thank you, Sam Altman. Baud rate and clock cycle. If no complex encoding is used, example, one symbol equals one bit, then baud rate equals clock frequency. This means that for a serial system with, am I in the middle of the screen? I am. This means that for a serial system with a single wire, the baud rate is directly determined by the clock speed, not clock rate or clock frequency, clock speed. A system with the 1 megahertz clock cycle, 1 million cycles per second, and no multi-bit encoding will have a baud rate of 1 MHz, 1 million symbols per second. Baud rate with multiple wires. The baud rate represents the same regardless of the number of wires. However, bit rate increases with more number of wires. Yes. Yeah. Now, the clock cycle of a processor can go up or down. How is that synchronized to have a stable baud rate? Yep, great question. A stable baud rate is crucial for reliable communication, especially when the processor's clock cycle varies due to high power saving mode, overclocking, or dynamic frequency scaling. Here's how systems maintain a stable baud rate despite a changing CPU clock speed. Baud rate generation using a divider. Most systems derive the baud rate from a fixed reference clock. They have their own clock separate from the CPU clock. This is achieved using a clock divider. Okay, baud rate frequency and clock frequency. Baud rate equals to baud rate divider. For example, if the processor clock is 16 MHz and we need a baud rate of 9600, the divider would be 1667 approx divider value. Even if the CPU, let's do this, 1600000, How many zeros are there? 6. 1, 2, 3, 1, 2, 3, 1, 6, 6 divided by 1, 6, 6, 7. Well, pretty close to 96000. Shit, there are quite a lot of things there. Now, even if CPU clock speed changes, the baud rate remains stable as long as the reference clock is stable. So it has a different clock. That is very revealing. Then UART baud rate generator. In microcontrollers and processors, the universal asynchronous receiver transmitter UART module has a dedicated baud rate generator that uses crystal oscillators, a precise external baud rate UART baud rate generator, universal asynchronous receiver transmitter module has a dedicated baud rate generator. So there is this device called UART baud rate generator, which is used to have a stable baud rate even for fluctuating processor clock speeds. Prescaler or fractional divider adjusts the baud rate to match standard values. There are standard values for communication. Okay, automatic baud rate detection. AArch. Some UART can synchronize automatically with an incoming signal. Advantage: since the UART baud rate is derived from a separate stable clock, it remains steady even if the CPU clock changes. Separate peripheral clocks, adaptive clocking, and synchronization compensation. Software compensation. Hardware solutions, adaptive clocking, and software compensations. Okay, guess we can move on. Where were we? We were reading about what is RS-232. That is how this all started. And RS is recommended system 232, which is used for communicating between different devices in a processor. Not in a processor, but in a computer. A processor is just a single core or multiple cores which communicate with other devices like microcontrollers, input output ports, or memory, or yeah, that is about it. Input out von Neumann architecture. Clock management devices. That is too bright. Very simple computer systems can be derived by a single clock. Most devices, including the CPUs, are designed as state machines. Yes, state machines. The clock device sends a square wave signal at fixed frequency to all devices that need it. The clock signal tells the device when to transition from the current state to the next state. Without the clock signal, none of the devices would do anything. None of the devices would do anything. And without the clock, none of the devices would do anything. Yes, because they would be stuck in a single state. They would have nothing to tell to give them the new state and thus process the new output. More complex computers may contain devices which need to run at different rates, like output or input devices, which need a stable baud rate. The This requires the system to have separate clock signals for each device or group of devices. System designers often solve this problem by adding a clock manager device to the system. This device allows the programmer to configure the clock signals that are sent to other devices in the system. Figure 11.7, this one, shows a typical system. The clock manager, just like any other device, is configured by the CPU, writing data to it. its registers and using system bus. This, where is the clock? Here I have the system bus and here is my clock manager. This can synchronize the system bus and give different clock signals to different input output devices and to CPU and to cache. Okay. And I can configure what signals to give at what times. The Raspberry Pi clock manager. BCM28XX. The BCM28XX system on chip contains an ARM CPU and several devices. Some of the devices need their own clock to drive their operation at correct frequency. Some devices, such as serial communications receivers and transmitters, need configurable clocks so that the programmer has control over the speed of the device. The programmer has control over the speed of the device so that they can change the baud rate if needed, and yes, they can tell a sensor in how much intervals to update its state according to the environment and give that state back to the processor. To provide this flexibility, allow the programmer allow the programmer to have control over the clocks. For each device, the BCM2800 includes a clock manager device which can be used to configure the clock signals driving the other devices in the system. The BCM28XX includes a clock manager device, which can be used a clock manager device like like this one, clock manager device, which can be used to configure the clock signals driving the other devices in the system. Okay, the Raspberry Pi has a 19.2 megahertz oscillator which can be used as a base frequency for any of the clocks. Okay, this frequency can be used as the base frequency, and okay, the BCM 28XX also has three-phase locked loop circuits. Three-phased locked loop circuits that boost the oscillator to higher frequencies. Table 11.7 shows the frequencies that are available from various sources. Number, some sort of, this is a 4-bit register. Numbers are ranging from 0 to 15, therefore 4-bit, and these are the frequencies that can be achieved, and I do not even want to pronounce this thing, GND, and clock stopped. Okay, and here are some offsets for clocks, specifically for BCM, BCM28XX. Each device clock can be driven by one of the PPLs, Public Legislature Assembly, not L, Public Legislature League. Yes, legislature in a democracy at least is controlled by the public. And yeah, and legislative assembly is also controlled by the public, but it is more, uh, it is not more, but it is legislature for the state, not for the central government. Among the clocks controlled by the clock manager devices are the core clock CM VPU, the system clock PM time, prime time, which controls the speed of the system timer, the GPIO clocks, which are documented in the Raspberry Pi peripheral documentation. Okay. Mhm. There is documentation for Raspberry Pi, and what the heck is this mean? Um, A equals hello, B equals world, A plus C equals A plus B. Okay. Wrong. A plus, there has to be a space in between. Yes, there has to be a space in between. Now, Raspberry Pi 3 documentation for programmers. Raspberry Pi documentation getting started again. Getting started. Raspberry Pi OS. There is just documentation for it, and which is like actually crazy. Mouse, I can connect a mouse to it. I can connect a keyboard to it, just like that. And this is a woman who is doing all of this. That does not change anything. It is just more inspiring. And Ethernet on all the things. This is amazing, right? Click choose device, and I can connect it to my Raspberry Pi just like that. Raspberry Pi imager. How do I connect? Ah, install an operating system. Edit. I can edit all of this on GitHub and make a pull request. That is just crazy how to set up a Raspberry Pi. But I need a Raspberry Pi. I do not have a Raspberry Pi. Raspberry Pi. Config.txt legacy, the Linux kernel. I can install the Linux kernel on a Raspberry Pi. All of this is just crazy stuff. Now, moving on. Serial communications, yes. There are basically two methods for transferring data between two digital devices, parallel and serial. Parallel has multiple wires, serial bit by bit. Like, of course, bit by bit, but only one bit at a time. Parallel communications use multiple wires to carry several bits at one time. Parallel communications typically include extra wires to carry timing information. Parallel communications are used for transferring large amounts of data over very short distances. However, this approach becomes very expensive when data must be transferred more than a few meters. More than a few meters. Serial, on the other hand, uses a single wire to transfer the data in bits one at a time. When compared to parallel transfer, the speed of serial transfer typically suffers. Okay, however, it uses much fewer wires. The distance may be greatly extended, reliably improved, and cost vastly reduced. Okay, but what if I am using parallel communication method with a single wire? And how can I achieve that? By not using a steel wire, which can only contain a state up or low, but by using an optical wire which carries light, and light can contain multiple wavelengths at the same time, and at the other end the combined homogeneous state can be seen, and then using Fourier transformation each individual sine wave can be extracted, and thus you got multiple frequencies at the same time. Well, let's see. Using a optical wire, I can I can send water. Using an optical wire. NEI. Yes. Using an optical wire, I can send light wave. No, I can send EM wave across a wire, and since EM waves, since an EM wave can be a combination of multiple sine waves of different frequencies, can be a combination of homogeneous or superposition, not combination, uh, superposition TIO of multiple sine waves of different frequencies, and at the receiving end that superposition of waves can be decoded using a Fourier transform back into its individual sine wave frequencies, which originally combined to form that superposition, and thus through a single wire multiple data is is sent in parallel. Multiple data is sent in parallel. Question mark. Is that correct? Yes, you are describing a fundamental concept in frequency division. Oh, this is called frequency division multiplexing. At the end, I have a multiplexer which takes in a single input and gives out multiple inputs. Okay, and wavelength division multiplexing, superposition, and Fourier transform. An electromagnetic EM wave can carry multiple signals simultaneously as a superposition of sine waves at different frequencies. At the receiver, a Fourier transform or filters can decompose this superposition into its original component frequencies, which originally came together to make this superposition of waves. Each frequency can independently carry data effectively, allowing parallel transmission over a single optical fiber. How this enables parallel data transmission. Hmm. Since different frequencies do not interfere as long as they are well separated, we can assign different data streams to different frequency channels, send them all at the same time over the same wire at the receiving end, and extract the original data streams by separating the frequencies. This technique is used in various communication systems, including radio optical fiber networks. We will also be reading about networkings. I guess in about 6 months' time, I will start a series on networking. I have a very good book called Networking, a Top-Down Approach, which teaches about networking and also has good questions. And I will be reading that. That is a cool book, and I will be taking my sweet time understanding every networking concept. That is cool. Now, multiplexing techniques. There are two key techniques for achieving this in practice: a frequency division multiplexer. There are two key techniques for achieving this in practice. Frequency division multiplexing. In electrical signals, we assign different frequency bandwidths to different signals. Different frequencies mean different signals. Each frequency carries a separate data stream, and multiple streams are sent simultaneously. Okay, different data streams, different data streams are assigned different frequencies, and thus different frequencies are combined as a superposition and sent through, and then at the other end those frequencies are decomposed from each other, and we get all of the original frequencies, and each single frequency carries a single data stream used in radio broadcasting, cable TV, and DSL internet. DSL. What was DSL? Digital service. Shit. DSL. DSL full form. What was DSL? Direct supply digital subscriber line. Digital subscriber line. Yes, digital subscriber line, which person can buy from ISP and have a modem installed at their home, which to which they can connect and access internet. It's like basically a Wi-Fi, but Wi-Fi which does not depend on optical cables. Generally nowadays, Wi-Fi use optical cables to get data to your house from the service provider, from the ISP, but digital server subscriber lines use physical metal wires, not metal, but you know, conducting wires which carry electrical information in electrical form. But today's Wi-Fi, they carry information in optical form. That is the difference. Wavelength division multiplexing. WDM used in optical fibers. Instead of electrical frequencies, different colored wavelengths of light are used in an optical fiber. Each color carries an independent data stream. The receiver uses prisms or diffraction grating to separate the wavelength and receive the original signal. Example of fiber optic using this can carry 100 plus different wavelengths, each transmitting 10 GB per second, having a over 1 plus TB per second, TBps, on a single fiber cable. That is just crazy technology that we humans have managed to achieve somehow. One of the oldest and most common devices for communication between computers and peripheral devices is the universal asynchronous receiver transmitter, or UART, which we just read about here somewhere. UART, about rate generator. Universal, the R and T stand for receiver and transmitter. What is asynchronous? Universal asynchronous receiver transmitter. Universal uni, universal asynchronous receiver and transmitter, or UART. The word universal indicates that the device is highly configurable and flexible. UARTs allow a receiver and transmitter to communicate without a synchronizing signal. The logic signal produced by the digital UART typically oscillates between 0 volts for a low voltage and 5 volts for a high voltage, that is positive logic. And the amount of current that the UART can supply is limited. For transmitting data over long distances, the signals may go through a level shifting or amplification stage. The circuit used to accomplish this is typically called a line driver. This circuit boosts the signal provided by the UART and also protects the delicate digital outputs from short circuits and signal spikes. Various standards such as recommended standard this, recommended standard this, recommended standard this define the voltage that the line driver use. For example, 232 standard specifies that the voltage should be this and this and this and this. Okay, the stream is not stuck, going absolutely okay. There are other things about UART and all that, which I do not need to read right now. And Raspberry Pi has its own UART, universal asynchronous receiver and transmitter, which I can just skip right now because I do not have to read about it and do not want to. Not more like I do not need to. This is maybe I might want it. I do not have a Raspberry Pi, so just maybe I might want it at some point. We can go through the chapter summary. The chapter has ended. All input and output is accomplished by using devices. By using, of course, devices like output monitor and input keyboard. There are many types of devices, and each device has its own set of registers which are used to control the device. The programmer must understand the operation of the device and use of each register in order to use the device at a low level. Computer system manufacturers usually can provide documentation providing the necessary information for low level programming. The quality of documentation can vary greatly, and a general understanding of various types of devices can help in deciphering poor or incomplete documentation. Poor The quality of documentation can very greatly, and general understanding of various types of devices can help in deciphering poor or incomplete documentation. There are two major tasks when programming devices at register level is required: operating system drivers and very small embedded systems. Operating system drivers drive drivers. These drivers provide an interface for an operating system to interact with a device. They can tell they provide an interface for the operating system to communicate with the device. So I as an assembly programmer can tell that driver, a specific driver, to do something, and that driver will make the call to that device on my behalf, so that I do not have to understand the integrities of that device and just can contact the device by using the interface. This is like abstract data types, objects. Operating systems provide an abstract view of each device, and this allows programmers to use them easily. However, someone must write that driver, and that person must have intimate knowledge of the device. On very small systems, uh, there may not be a driver available. In that case, the device must be accessed directly, even when an operating system provides a driver. Sometimes it is necessary or desirable for the programmer to access the device directly. For example, some devices may provide modes of operation or capabilities that are not supported by the operating system driver. Linux provides a mechanism which allows the programmer to map a physical device into the program's memory space and thereby gain access to the raw device registers. And that is the only way I can contact with a device, by modifying and reading its registers. Pulse modulation is a group of methods for generating analog signals using digital equipments. Pulse modulation is commonly used in control systems to regulate the power sent to motors and other devices. Pulse modulation techniques can have very low power loss compared to other methods of controlling analog devices, and the circuitry required is relatively simple for pulse modulation, which is used for generating analog signals using digital equipment. The cycle frequency must be programmed to match the application. Typically, 100 Hz is adequate for controlling an electric heating element, while 120 Hz would be more appropriate for controlling an in, incandescent light bulb. Large electric motors may be controlled with a cycle frequency as low as 100 Hz, while smaller motors may need frequencies around 10,000 Hz. It can take some experimentation to find the best frequency for any given application. Most modern computer systems have some type of universal asynchronous receiver and transmitter, that is UART. These are special communication devices and are meant to provide communications, while other systems using RS-232 most commonly, or some other standard serial protocol. Modern systems often have a large number of devices as well. Each device may need its own clock source. Each device may need its own clock source so that it can communicate at its own baud rate and not depend on the clock speed of the processor, which can vary over time due to efficiency mode, power saving mode, or due to power saving mode means reducing the clock speed of the processor. That is cool knowledge to have. Although two systems may have different UARts, the devices perform the same basic functions. The specifics about how they are programmed will vary from system to system. However, there are always enough similarities between devices of the same class that a programmer who is familiar with one specific device can easily learn to program another similar device. The more experience a programmer has, the less time it takes to learn how to control a new device. Yo, exercises, and then we can move on. Running without an operating system, and I am planning maybe we can complete this chapter today. That would be cool because tomorrow I can start with something else, something new. Oh shit. This might be the last stream that I am streaming about assembly. Well, not a dedicated, this might be the last dedicated assembly stream. Let me see. Are there any viewers, which probably aren't, but maybe just in case? Nope, of course, of course. And yes, explain the relationships and differences between device registers, memory locations, and CPU registers. Okay, CPU registers are the registers which are inside the processor itself, the very fast access memory which is inside the processor itself. And then memory locations is the memory which is outside the processor and is much larger than the amount of memory that is inside the processor, but is comparatively slower than the registers. And this is typically called RAM. Then we have device registers. These are registers which store bits inside a device itself. For example, a keyboard has its own registers. And if I want to communicate with the keyboard, I can manipulate the bits in the registers which are present inside the keyboard. That is the way. So, keyboard is just a memory location which can be accessed through assembly. So, keyboard is just a memory location which can be accessed writing assembly code by writing assembly code. Why is it necessary to map the device into your program's memory before accessing it? Under Linux, would this step be necessary under all operating systems or in the case where there is no operating system and our code is running on the bare metal? It is necessary to access it is necessary to map the registers of a device onto your program's memory because that provides a way for you to access that device's registers. And by accessing those registers, you can communicate with the device. You can send data and receive data, and that is the only interface that you get to control a device by manipulating its registers. So, and to get access to its registers, to actually manipulate the registers, you want them to be mapped onto your program's memory. What is the purpose of a GPIO? GPIO device stands for General Purpose Input Output. And a GPIO device is a device which is in a computer and it has its own registers like any device. And on its physical output side, that GPIO has several pins, physical metal pins, which can be in different states, either low voltage, high voltage, or yeah, or some more complicated states. And those states are determined by the patterns of bits in GPIO's registers. So, if you want to turn on a light and you need high voltage on a particular pin and low voltage on another pin, so that you have connected that light onto those two pins, then you can manipulate the bit pattern in the GPIO's register to provide that amount of voltage that you need to turn on that light bulb, and that works. Thus you can thus you are in a way directly or indirectly accessing the state of the light bulb using the GPIO. general purpose input output device. Okay, I'm not gonna do this one. Draw a circuit diagram showing how to connect a push button switch to GPIO 23 and an LED to GPIO 27 on the Raspberry Pi. First of all, I do not have a Raspberry Pi. Second of all, I cannot get into this because I do not have a Raspberry Pi. Third of all, since I do not have a Raspberry Pi, I won't be able to do this. And I do not find any incentive to actually understand all of this about Raspberry Pi because I do not have a Raspberry Pi. And when I do, I will be much more interested into doing this. And it would be much easier for me to understand all of this if I were to have a Raspberry Pi. Assuming the system is wired according, but I will buy a Raspberry Pi in due time when I have more money. Well, I do have money, but I want to spend it on something else. Assuming the system is wired according to the previous exercise, write two functions. One function must okay, that is the same thing. Write code necessary to route output from this to this, yeah, on a Raspberry Pi. Okay, write ARM assembly code for making some changes to the GPIO device and thus having a contact with other device which is connected on top of the GPIO. Okay, write a function for setting PWM clock on Raspberry Pi. That is okay. Now we can move on to the next chapter, which is apparently the last chapter. This is at page number 445. And what are the topics that it has? Expecting exception processing. I do not understand what exceptions are, so that would be cool. AArch64 execution and exception status. That would be cool. And AArch64 vector table. Okay, I will look into that. Of course, well, since I'm reading it. Well, since I'm reading it does not mean that I will look into that. The boot processor. Make it a bit larger so that you guys can see. Main program. Wait, it was the boot processor? Right, a bare metal program. That is cool. But again, the thing is, I do not have a place where I would do that to practice it and generate my interest in it. I cannot learn football by watching others play using an interrupt. Mhm, 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 mhm. There is a lot of assembly code and ARM processor profiles. That is a cool thing to learn about processor profiles. And then the chapter has ended at page number about 80 and it is started at 64, if I remember correctly and not stupidly. 45, not 64. A horrendous mistake. The previous chapters assumed running without an operating system, so that I cannot call a syscall. If I'm running without an operating system, I cannot call a syscall. I would actually have to do everything on my own. That is crazy. Now, yes, and we move on. The previous chapters assumed that the software would be running in user mode under an operating system. Sometimes it is necessary to write assembly code to run on bare metal, which simply means without an operating system. Bare metal means without an operating system. For example, when we write an operating system kernel, for example, Linux or Darwin, or what was the kernel for Windows? Windows kernel name NT kernel. It must be run on bare metal and a significant part of the code, especially during the boot process, must be written in assembly. Coding on bare metal is useful to deeply understand how the hardware works and what happens in the lowest levels of an operating system. There are some specific significant differences between code that is meant to run under an operating system and code that is meant to run on bare metal. We would understand it well a bit from this chapter and a bit when we will be writing our own operating system in some stream in Rust using Vim. That is crazy. And where will I run that operating system? On a virtual machine? Yes, on a virtual machine. I will have to look up what virtual machines are and how they operate. That would be cool. Then I would have the power to run things that I do not have. But it is much closer to reality if I'm not using a virtual machine and actually have the bare metal stuff. But that is not always practical. So we will have to go with virtual machine. The operating system takes care of many devices for details for the programmer. For instance, it sets up the stack, text, data sections, initializes static variables, provides an interface to input and output devices, and gives the programmer an abstracted view of the machine. When accessing data on the disk drive, the programmer uses the file abstraction. The underlying hardware only knows about the blocks of data. The operating system provides the data structures and operations which will allow the programmer to think of data in terms of files and streams of bytes. A user program may be scattered in physical memory, but the hardware memory management unit managed by the operating system provides a virtual memory, allows the programmer to view memory as a simple memory map, such as Pyeatt 1.7. The programmer uses system calls to access the abstractions provided by the operating system on bare metal. There are no abstractions unless the programmer creates them. That would be cool doing bare metal coding. I really want to have a Raspberry Pi. However, there are some software packages to help bare metal programmers. For example, newlib is a C standard library intended for in bare metal programs. Its major features are that it implements the hardware implement independent parts of the standard C library. For I/O, it relies on only a few low-level functions that must be implemented specifically for the target hardware. It implements the hardware-independent parts of the standard C library. For I/O, it relies on only a few low-level functions that must be implemented specifically for the target hardware, and many target machines are already supported in the new lib source code. To supply a new machine, the programmer only has to write a few low-level functions in C and assembly, which will initialize the system and perform low-level I/O on the target hardware. Okay, okay. Main process. This is something exception handler. Here is my main process. Here it raised an exception, and I am looking in the diagram without reading the thing first, which is a crazy feat. Yes, my mouse has started working now. Hmm. Shit, my camera seems to have stopped. Why the heck? Okay, I'm trying to fix it. What do I do? Let me hide my screen for a sec. And fixing. Fixing. Wait, this should not have happened. Um, yes, this I am right now doing FaceTime with my phone's camera, and that is not working. My phone's camera is not available. My laptop is unable to connect to my phone somehow. Shit. Even though they are connected to the same Wi-Fi, my laptop is unable to connect to the phone due to some reason. Is it because I have some update on my laptop or maybe on my phone? I gotta see it. Checking for updates. General software update. I do not have any update on my laptop. I do not have any updates on my phone. I just updated them a few days ago and it is not working somehow. Why the heck does that happen? And I do not want to close OBS and then start it. My stream will be stopped. So what I can do is um wait. Yes, this is another stream. This is another. This is another. This is another. And I due to some reason have this is Jordan Peterson stream and should you can hear the voice. Wait, no, you cannot hear the voice. That was my voice. What is this image? Should I also have an image in the background? That is. Shit, what the heck is happening? Okay, stream is not working. Es funktioniert nicht. Okay, I will continue with my laptop's camera, which is a shitty camera, but still that is something. At least um, video capture device, video capture, and device would be Jatin's iPhone is not working, right? FaceTime HD. Yep, that is me. You can have me here. But wait. I want this to work, but you guys do not have to, should not care about this. This is a me thing, which me, the content creator, has to get right. And you guys should not be going through this process. Nope, not working. Wait, then I will just use that. Mm, wait, yep, I can crop this a bit to remove the books from the background. Where can I crop it from? Hmm. Scale filtering, blend mode, deterrence, transform, copy, rotate, flip, stretch, center, vertical, order, rename, set color, copy, add crop, no, preview scaling, full screen. There was a way through which, wait, nope, nothing on my phone. Nope, phone is not working. I will have to be using this, and it is not even cropping. So this is what you guys will get. And now we can begin our last stream on assembly. Exception processing. Many early computers were not capable of protecting the operating system from user programs. That problem was solved mostly by building CPUs that support multiple levels of privilege. By building CPUs that support multiple levels of privilege for running programs, almost all modern CPUs have the ability to operate in at least two modes. Processors, CPUs, can run in a user mode, is the mode that normal user programs use when running under an operating system, and privileged mode is reserved for operating system code or exception handling. There are options operations that can be performed in privileges mode which cannot be performed in user mode. Many bare metal programmers consist of a single thread not programmers, consist of a single thread. Programs consist of a single thread of execution running in user mode to perform some tasks. This main program is occasionally interrupted by the occurrence of some exception. The exception is processed and then control returns to the main thread. The main thread usually returns with runs with the user privileges, and exception handle processing is done in the privileged mode. Like in this diagram, if the flow of the program is downwards, then the main process was going at some point there was an exception. Then exception was handled during and some work was done, handle the exception, save user mode registers, then restore user mode registers like we do store pair and restore and load pair. And figure 12.1 shows the sequence of events when an exception occurs in such a system. The main program typically would be running with the CPU in user mode. When the exception occurs, the CPU uses the vector table to find and execute the appropriate exception handler. Okay. When an exception occurs, then the CPU looks into the vector table. Vector table. There is a table called vector table, which maps each exceptions code uh, like exception code like exception number 50 to a set of instructions which must be run when that exception occurs. Different CPU architectures have different methods of implementing vector tables, but all modern CPUs support some type of vector table. The exception handler must save any registers that it is going to use, ex- execute the code required to handle the exception, then restore the registers. When it returns to the user mode process, everything will be as it was before the exception occurred, as if the exception never occurred. The user mode program continues executing as if the exception never occurred. So there can be exceptions in exceptions. Exception processing with multiple user processes. Here is a user process. More complex systems may have multiple tasks, threads of execution, or user processes running concurrently. In a single processor system, only one task thread or user process can actually be executed at a given instant, but when exceptions occur, the execution handler may change the currently active task thread or user process. This is the basis for all modern multiprocessing systems. If a thread is running on a core and an exception has been raised, then the state of the processor at that point is captured and stored maybe on the stack, and then the exception handler code is fetched from the vector table and is runs in the processor, and after that code, the original state that the processor was in is fetched from the stack, put into the processor, and the main thread which caused the exception starts executing again. That makes sense, I guess. This is the basis for all modern More complex systems may have multiple tasks, threads of execution, or user processes running concurrently in a single processor system. Only one task thread or user process can actually be executing at any given instant. But when an exception occurs, the exception handler may change the currently active task thread or user process. The exception handler at any instant when an exception occurs, the exception handler may change the currently active task thread or user process. This is the basis for the modern multiprocessing systems. Figure 12.2 shows how an exception may be processed on such a system. It is common on multiprocessing systems for a timer device to be used to generate periodic interrupts, which allows the currently active task thread or user to be changed to a fixed state. I don't get the second half of that. Privileged mode is entered automatically by the hardware when certain exceptional circumstances occur. For example, when a receives hardware device needs attention, it can signal the processor by causing an interrupt. It can signal the processor by causing an interrupt. When this occurs, the processor immediately sets the appropriate exception level and begins executing the IRQ IRQ execution handler function from vector table. The exception handler or their addresses are stored in a vector table at a known location in memory. Yes, vector table stores the exceptional handler codes at a known location in the memory. When an exception occurs, the CPU automatically uses the vector table to find and execute the appropriate exception handler function. Yep, yep, that makes sense. So a processor can run in two modes, either in user mode or in privileged mode. And when an exception occurs from the user mode, the processor switches to the privileged mode and fetches the exception handler code by looking up the vector table for that is exception which has been raised, and then it executes the exception handler code and starts the main thread in the user mode which made that exception. AArch64 execution and exception states. Okay. In AArch64, the AArch64 processor provides two major modes of operation, referred to as execution states. They are 32-bit Arch. The AArch64 processor provides two major modes of operation, referred to as execution states. Two major modes of operation, referred to as execution states. They are 32-bit Arch 32 state and 64-bit Arch 64 states. Both of these execution states provide privileged modes and a user mode. The Arch32 execution state allows the processor to execute code written for a V7 older processor. Okay, so what that I suppose means is that in Arch64 I can run 32-bit Arch32 instructions when the processor is in 32-bit Arch32 state, and I can also run the latest 64-bit Arch instructions. The Arch32-bit state can run ARM v7 instruction set. That is crazy that you can run two types of instruction sets in the same processor. Although there might not be that much difference between the two, but still, that you can do that is crazy. And Apple has made its own design to implement all of these. That is crazy. Otherwise, people just use ARM Cortex design to manufacture processors based on ARM instruction set. Now, in the AArch64 execution state, there are three privileged modes and one user mode. Okay, there are three privileged modes and there is one user mode. These referred to as exception levels. These are referred to as exception levels. The higher the exception level, the more privilege the code has. Okay, typically the system uses the exception levels as follows. EL0, exception level 0, is for you user applications, then exception level 1 for OS kernel. Shit, level 1 itself has the kernel running on it and other privileged code. Then exception level 2, which is a hypervisor support for virtual machines. That is crazy. Virtual machine code has more access to the processor than the installed kernel. EL3, secure monitor, manage survey security contexts. So I guess this EL3 is the level which is controlled by the hardware processors, hardware people who make the processors. And yes, at least I'm not stuck. And let me do one thing. FaceTime HP background. That is crazy. That is a crazy background. Let me change it. Can I change? Yep, I have multiple background. Ah, that is too dark. That is too bright. Rainbow? Nah. I can add. Wait, let me add something here. Let me add a background. Choose a background and add it. Downloads. I will find a crazy background. Well, I will not. Let me just see. WebE is. I don't know what WebE is. No, I do know what WebE is. WebE is web install things from web. And I might have a Vikings background, which is cool. It is like pretty cool for someone to have a Vikings background, or maybe the Berserk background, which is also pretty cool. Or Gargantua. How about this one? How about this? How about this? That is a cool background. Okay, yeah, that is fine. That works. That is fine. Fine background. That works. Okay, we will go with that for now. Yes, I wanted to know what are exceptions. What are exceptions? What are exceptions? Exceptions are unexpected events or errors that occur during the execution of a program, disrupting the normal flow of instructions. They usually arise when the program encounters a situation that it does not know how to handle, such as division by zero, accessing an invalid memory address, trying to open a non-existent file, running out of memory. Types of exceptions. Hardware exceptions. Exceptions can generally be classified into hardware exceptions and software exceptions. Hardware exceptions. These are generated by the CPU when it encounters an issue at the hardware level. Examples include division by zero, segmentation fault, invalid memory address, page fault, trying to access memory that isn't currently mapped. Okay. Hmm. These are hardware exceptions which can be raised by a program. Okay. And then I have software exceptions. These occur when a program runs into an error due to logic or input issues. Due to logic or input issues. Null pointer exception, accessing an uninitialized pointer. Okay, yeah, a pointer which does not point to anything. That is, it is uninitialized. Array index out of bound. That is just segmentation fault. File not found. Trying to open a missing file. Okay, how are exceptions handled? Low level assembly and C. In assembly and C, exception handling is typically done using interrupt handlers and return codes. The OS or CPU detects the error and jumps to an exception vector, a special handler code. In high-level languages, Python and Java high-level languages use a try-catch or try-except mechanism to handle exceptions. In Python, we have try to divide by zero, and if you get an exception called zero division error, then print this. In C, try, throw, std, runtime error, something went wrong, catch. Oh, uh, in the try block itself, I'm just throwing the error. Throw in the standard library a runtime error with this string, okay, and catch const exception and e, and in this use the standard abstract data type ADT, and its count property takes the input caught exception, which takes the input e dot what. I do not understand C++. I've never written C++ code, so that was fine. Okay, so what I understand is that there are two types of exceptions. First, exceptions that take place on the hardware level. On the hardware level, that is accessing some memory location which you are not privileged to, or registers dividing values in registers which might contain zero. So I can okay. Um, there are two TWO, two types of exceptions it seems. First, which take place on the hardware level and cause the main thread to stop, and the vector table is queried to solve to run the exception handler code to run the exception handler code. Yep. And then there are exceptions which arise in programs in higher level languages, and for these exceptions the vector table is not queried and the handler code is defined in the high level language program itself. Is that correct? Yes, exactly. You are correctly identifying two broad categories of exceptions: hardware exceptions, CPU level. These occur directly at the hardware level due to invalid operations performed by the CPU. When a hardware exception occurs, the CPU stops executing the current instruction and jumps to a predefined exception handler. The vector table stored in the special memory location is queried to determine the correct exception handler to execute. These are managed by the operating system or firmware. By the operating system or firmware. Firmware is the code that is on the ROM by and put there. It is put there by the manufacturer. And wait. One more thing. I can do a crazy thing if, well, first of all, turn on studio lights, which is much better. And second of all, can I do center stage in here? Nope. I have portraits. So why can I not see it if laptop is still connected to my phone? Can I connect to it now? Nope. No connection. Nope. Can't connect. Somehow just let me try to use FaceTime for connecting. Nope. Nope. Not working. Okay, it is fine. I will be using this only. Yep. Exception handling and in hardware exceptions. Exception handling. Division by zero, CPU generates a fault when attempting to divide by zero. Segmentation fault, invalid memory access. Page fault, when accessing memory that is not currently mapped in the page address. Page fault, that is I might be getting out of the bounds of the page. The OS handles it. Illegal instructions that don't exist and are just a figmentation of your mind. Software exceptions handled in high-level code. These occur inside a program when something goes wrong due to logic errors, bad input, etc. The CPU does not stop executing or query the vector table. Instead, the language running Python, the language runtime Python, Java, C++, etc. provides built-in exception handling mechanisms. These exceptions are handled within the program itself using try, catch, try except blocks. Examples of software exceptions: null, no, null pointer exception. Dereferencing a null pointer in C++ leads to an exception: array out of bounds, file not found. Handling mechanism: the run environment handles these exceptions without CPU level interventions. Hmm. Hmm. This makes sense. Two types of exceptions there are, and then there are multiple modes in which the processor can run. That is multiple privileges. Privileges or privileged. Privilege Lig. Privilege modes. Multiple privilege modes, and in Arch 64 there are four, and privilege level, right? Privilege, that is what it is called. EL, exception level. exception EL0 for user and EL1 for kernel. EL2 EL2 is for hypervisor. I can just copy this thing. This. So there are privilege levels which have more control over the processor than the kernel, which is crazy. And support for virtual machines. The EL2 level has level which runs code for virtual machine has more privilege than the kernel. If that is the case, then if someone can hack into my virtual machine, then they have more control over the processor compared to if they had hacked the kernel, the OS, the OS kernel, which seems uh, ironical since virtual machines are there to run code in a safe environment which doesn't affect the main OS. Let's see. Yes, that realization is quite fascinating, but there is an important distinction to understand regarding privilege levels and security in virtualization. Understanding the AArch64 exception levels (ELs), the four exception levels in ARM64 are arranged in a hierarchical manner, with higher levels having more control over the system. Level 0 for user mode, 1 for kernel mode, and 2 for manages virtual memory, virtual machines. Okay, KVM security monitor handles security contexts, trust zone, secure boot, trusted execution. Why does EL2 have more privilege than EL1? EL2 is designed for virtualize virtualize EL1. That means EL2 creates and manages virtual machines. The guest OS running inside a VM operates at EL1 as if it were the host kernel. EL2 controls what the guest OS can access, ensuring hardware isolation. Key points: even though EL2 has more privilege than EL1, it does not mean a compromised VM automatically gives the attacker control over the host machine over the host system. Does hacking a virtual machine give more control than hacking the kernel? Not exactly. While EL2 is more privileged than EL1, virtualization platforms implement strict security measures to ensure VMs remain isolated. If an attacker hacks a VM EL1, then they usually do not get access to the hypervisor. It's called hypervisor EL2. To break out, they would need to exploit a vulnerability in the hypervisor. However, if an attacker hacks the OS kernel of the host machine, not a VM, they control everything running at EL0 and even escalate privileges to EL2 if there is an exploit. How virtual machines stay secure? Hardware assisted virtualization. Hardware assisted virtualization ARM provides stage 2 page tables so that the EL2 can control all memory access by EL1, preventing direct access to hardware. The kernel does not has direct access to hardware. It has to access hardware by calling up EL2 function call VM escape protection. The hypervisor enforces strong isolation, preventing a VM from directly accessing another VM or the host. Security boost and integrity checks. EL2 secure monitor can verify that EL2 is running trusted code. Hmm. Okay. Conclusion. Follow up. Would you like to explore more? Okay. So EL2 is there to manage EL1 level for a VM and makes it so that the VM kernel VM kernel guest feels guest works as if it were working as the host, and this and and EL2 also separates memory for the VM and gives the host the remaining memory, and neither the host kernel or the guest kernel know that they only have partial memory access. Is that it? No? Yes, that is exactly right. EL2 makes each guest OS believe that it has full control over the system, even though it is actually being restricted and managed by the hypervisor. Let's break it down step by step. Okay, how EL2 hypervisor mode manages EL1 guest kernel virtual machining for virtualizing EL1 for VMs. EL2 creates an environment where the guest OS running at EL1 in the VM thinks it has full access to the CPU and memory. In reality, the hypervisor intercepts privileged operations and translates them safely. Memory virtualization and isolation. Memory virtualization and isolation. EL2 uses state to transition tables to control which part of memory a VM can access. The guest OS EL1 in the VM manages stage 1 page table, but there are further these are further translated by EL2. Okay, the guest OS is unaware that EL2 is restricting its memory. It only sees the virtual address space. Yes, it only sees the virtual address space, which is mapped onto the physical address space by the VM by VM2. So virtual memory is not handled by the OS, which is crazy. So um, the code that runs at the EL2 level is not a part of the host kernel, but is a part but is written by the processor manufacturer manufacturer, by the hardware company. Not necessarily the code running at EL2 level is not always written by the processor manufacturer. It depends on the system and the hypervisor being used. Who writes EL2 code? Bare metal EL2 processor default code. Some processor ship. Wait a minute. Everything is going right. Everything is going right. Except that I do not have a good camera and uh, the part here inside is not getting trimmed correctly. My hands are not getting trimmed correctly. Bare metal EL2 processor default core. Some processor chip with a built-in firmware hypervisor in EL2. Some processors ship with a built-in firmware hypervisor. Yeah, that is called firmware. Yeah. This can be used for simple virtualization without needing an external hypervisor. Example: some ARM embedded systems use a basic hypervisor for security purposes. Custom hypervisors, software based. In most general purpose systems like Linux, Windows, or with virtualization, the EL2 code is provided by the software, not the processor manufacturer. By the software. What software? The hypervisor software runs at EL2 and controls guest VMs. Example: KVM, Linux kernel virtual machine. KVM, LKVM, or Zen runs in AL2. Proprietary hypervisors like game consoles run proprietary hypervisors at EL2. These are often closed source and tightly integrated with the hardware. What hypervisors run at EL2? There are some examples of software run at EL2. KVM, this Apple's hypervisor, which is proprietary and firmware based. Versus bare metal EL2 hypervisor is the EL2 code separate from the host kernel. Yes, the hypervisor EL2 is separate from the host OS2. The host OS does not control EL2 directly. The hypervisor EL2 manages the host OS as just another EL1 instance. If no virtualization is used, EL2 is mostly idle or runs minimal management code. Or runs minimal management code. Key takeaways. Follow up. Would you like a detailed follow up? I think I have a good understanding, a fine understanding that works at this point. And what is that? That there are multiple levels that a processor can work at, right? And there is code for each level. The program code, for example, Chrome or any other application code, is runs at the user level, and then there is the user level is represented is as EL2, and EL1 represents kernel level, and this is the level where the operating system kernel works. And then there is a EL2 level, which runs at a higher privilege mode than the host kernel. And the EL level 2 code is written either by the hardware manufacturer, but not necessarily. It is more broadly written by in Linux by it is a software which can be downloaded, and this software will run at EL2 privilege level. And for Linux, it is Linux kernel virtual machine, which is open source software. And this EL2 software manages memory and privileges access for the kernel for the host and for a guest kernel for running virtual machines on your code. That was it. Now, the major difference between EL0 and higher levels is that the code executing in EL0 cannot access system registers. Ah, So the assembly code can access system registers, therefore it is running at a higher privilege level, it seems. EL1 can access most system registers, EL2 has additional privileges, and EL3 has all privileges. The only way that the processor can change from one exception level to a higher exception level is when an exception occurs. The only way the processor can move to a lower exception level is by executing an exception return instruction. When changing the exception level, it is also possible to switch between AArch64 and 32 instruction state execution state. So if I have exception handler code written in AArch32 that can also be used to handle an exception in the AArch64 based processor, because I can change mode during a change in exception level. The processor also supports two security states, security and secure and non-secure. Very original. EL3 is meant to manage the security state. EL2 is meant to provide virtual machine capabilities. In many situations, only EL0 and EL1 are required, and some processors may not provide EL2 or EL3. On power up and on reset, the processor enters the highest available exception level, runs the kernel, and goes down. Each exception level has its own stack pointer, which is crazy. Stack pointer and link register, saved process state registers. Process state regis- processed state register, saved process state registers. Table 12.1 shows the names of these banked registers. When the exception level changes, the corresponding link register and stack pointer becomes active and replace the user stack pointer and link register. Yes, also when an exception occurs, the current P state register is copied into the state saved process state register for for the exception level that is being entered. When an exception occurs, the current P state is copied into this register, which where N is the exception level being entered. Okay, the P state register is updated. The exception level stays the same or gets higher. The return address is stored in this. The program counter PC is set to point to the vector address, and if it is synchronous or S error exception, ESR ELN is updated with the cause of exception. To return from an exception, the return exception return instruction is executed. This instruction restores the P state from PS SPSR register, restores the program counter PC from ELR ELN. Okay, okay. Mhm. Hmm. And then there are calls, system calls for managing that. And now you're going to do vector table asynchronous. Yeah, that is cool thing to learn at assembly level. In AArch64, exceptions are divided into two major types, synchronous and asynchronous. Synchronous exceptions are synchronized with the CPU clock. With the CPU clocks. With the CPU clocks. This type of exception includes data aborts from MMU, Muslim Major University, permission alignment failures for load and store operations, service call instructions, and legal instructions. Asynchronous exceptions may occur at any time and may not be synchronized with the CPU clock. These exceptions include interrupt requests. Inter Okay, I want to see what are interrupt requests. Requests IRQ and FIQ from external devices. And do you I have sufficient time, more than sufficient time. What are interrupt requests, interrupt requests, IRQs. And let me go to the washroom for just a minute, and I'll be back in less than a minute, maybe in a minute. Not to stop streaming, but yo, me back. And now, where were we? Just taking a 2 minutes break gave me like a boost and refreshed me, which is cool. What are interrupt requests? Interrupt requests explained. IRQ seems like IRS, Income Revenue Service. An interrupt request IRQ is a signal sent to the processor to pause its current execution, sent to the processor to stop its current execution to handle an urgent task. It allows hardware devices and software to interrupt normal processing to request immediate attention. Types of interrupts: attention seeking processes. Interrupts can be categorized based on their source and how they are handled. Based on their source and how they are handled. From which, what are the things that caused the interrupt and how they are handled. Hardware interrupts. These come from external devices, example like keyboard, timer, network cards, etc. that need the CPU's attention. Oh, for example, pressing a key on the keyboard triggers an interrupt IRQ telling the CPU to read the key press. Huh. Two types of hardware interrupts. Maskable interrupts can be enabled and disabled by the CPU. Non-maskable interrupts (NMI) cannot be ignored. Used for critical events like hardware failures like a heart attack. Software interrupts generated by software programs to request service from the OS or signal an event. Example, a program calls an OS system function or a supervisor call using an interrupt like init this in for Linux system call. System calls. Exception types: syscalls, syscall program asks the OS to perform an operation using a software interrupt. Using a software interrupt, exception faults when a CPU encounters an error division by zero page fault, uh, which is caused by the program running in the CPU, and that is native to this processor. That is, it arises in the processor itself. How interrupts work: process flow. Interrupt occurs, a hardware device or software requests an interrupt. A hardware or a software requests an interrupt. Interrupts can be risen, risen, can arise from hardware or software. CPU saves state, registers, and program counter PC are stored to resume execution later. Vector table lookup. The CPU finds the correct interrupt service routine ISR from the interrupt vector table. All of this is so much work, and still I have a computer in front of me. That is crazy. ISR execution. The CPU runs the interrupt handler code. Interrupt completion. The CPU restores its state and resumes normal execution. ARM64 handles interrupts using different exception levels till 3, base down till 0. Interrupts. Okay. So let's say my processor has only a single core. Thus, it can only process a single instruction at a time, and different processes are running on uh, running running on it using time sharing methods. Now let's say I have a monitor and a keyboard connected to it, and what I press on the keyboard goes causes an interrupt, and the processor handles the interrupt by taking in the input key and storing it inside a buffer, and then updates the buffer for the monitor to match the new buffer, which has the latest key press. So I'm supposing that there are two buffers, one that stores the input by the keyboard, and then there is another buffer which stores the things that are being represented on the monitor. And then the monitor, and when the monitor buffer is updated with the new key, when the monitor buffer is updated with the new key, then the screen driver, the monitor driver also updates its state and shows the new key press. Now, if I were to press the keys very fast, even faster than a robot like you, then I would be repeatedly causing interrupts, which would keep updating the keyboard buffer but won't give any execution time to update the monitor buffer. Thus, I won't be seeing any changes on the monitor unless I stop pressing the keys so goddamn fast. How about that? You are on the right track while understanding how interrupts work, but there is an important point about interrupt handling and prioritization that ensures your system is not stuck in loop of handling keyboard inputs without being able to update the monitor. Let's see what that is. Key concepts in interrupt handling and prioritization. The CPU does not get stuck in an infinite interrupt loop when multiple interrupts are triggered. Example from key pressing key fast. The CPU has an interrupt priority mechanism and an interrupt service routine ISR ISA. There is ISA, not ISR. ISR income service. There has to be something that is income related with ISR. R is revenue and IS is income service revenue. That ensures that important tasks like updating monitor get time to execute. In most systems, interrupts are handled by some form of priority, meaning some interrupts like those from keyboard are handled quickly, but more critical tasks like updating the display are given priority or can be scheduled to run after the interrupt handling is complete. Time slicing and context switching. With the time slicing multitasking, the CPU does not focus only on the keyboard interrupts. The OS schedules processes in time slices so that every process, including the one that handles the updating the monitor, gets a chance to run. Even if you are pressing the keys rapidly, the system will quickly handle the keyboard interrupt. But once the interrupt is processed, it will context switch and give time to other tasks, including updating the monitor buffer. Interrupt latency and buffering. In reality, keyboard input is buffered. If you press a key very fast, the system typically has a buffer that stores multiple key presses. The keyboard interrupt may be triggered frequently, but once the interrupt service routine presses the keyboard and reads the keyboard and places it in the buffer, the OS can still update the monitor buffer as long as it gets the share of the CPU time. Buffering means that even if the interrupts are coming in fast, the CPU won't miss key presses because the keyboard buffer can hold multiple key events at once and the system can process them one by one without missing any key. How this system handles a rapid interrupts. Key presses. Interrupt triggered by key press. When you press a key, an interrupt is triggered. The keyboard ISR. I just saw that ISR thing. Interrupt service routine. The keyboard service routine interrupt service routine, that is a set of instructions which will begin executing when a key is pressed. No, a set of things, the instructions which will cause an interrupt from the device side. The interrupt and stores the pressed key in the buffer. Quick context switching. After handling the keyboard interrupt, the system context switches back to the monitor, update the task or any other task in the scheduler. The monitor driver then updates the display based on the new contents of the buffer. Multitasking. This continues as the system schedules tasks in the way that prevents one task keyboard interrupts from completely blocking another monitor updates. Buffer management. The keyboard buffer will hold this fast input and system will process them in turn, in turn, in turn. The monitor will keep updating the keys and will appear on the screen as the system processes the buffer. Why doesn't the screen stay frozen? Even though keyboard interrupts might be triggered in rapid succession, the monitor buffer updates will still happen because the system is designed to handle time sharing and manage multiple tasks, including input handling. The OS is structured in a way that fair access for the CPU for including each task. Okay, the CPU has time sharing, therefore the monitor will also have its bit of the pie, its own share of the pie. And if I do an interrupt while while some other process is being happening, and I keep causing an interrupt by pressing a key, that then those keys will be stored in a buffer, and the processor can not handle a interrupt at that point, but can take the inputs from the keyboard buffer at any time that it wants. Background tasks. Okay, that makes sense. That was interrupts. Now, AArch64 vector table, but I guess that is for tomorrow, and for today, that was it.